Welcome to this new tutorial. In this tutorial we are going to see how can we analyze the flexible bodies in the atoms. So you can find out the stresses deformation of flexible bodies during its motion. So how can we do that? So in this tutorial we are going to analyze flexible connecting rod of simple engine mechanism. For let's get started with our tool. This is a simple crank connecting rod and piston assembly. So this is assembly in SolidWorks. First we have to save it is in a parasolid format. So just go to save as. So save to some directory I have created as a flex model. So choose a format from here as a parasolid. Don't choose parasolid binary but choose parasolid and save. Okay, this model is saved. Now close the SolidWorks. So I am going to add-ons. So I will create new model. So I'm giving a title as a flex connecting rod. Let's say I will choose the working directory for this. Go to our folder. Here you will find, select this folder and OK. Now from file menu select import. Here you will see file type. So go drop down from this file type. You will find parasolid. So file to read, just right click here and choose browse. So this parasolid XD type file will be shown. Just open it and model name, right click here and from model just guess this flex R and click OK. So you can see this geometry is imported. So now it is in wireframe mode. Just click here, you will see in a solid format. Okay, that's fine. So just we'll go in model tree and we'll see every part here. This is a crank. You can see there is a only PSMAR, that is a position marker. First we have to apply material for each part. So you don't see any center of mass marker, that means material is not applied. So first go by one part. So piston head, just double click here. So you can see there is a mass is 0. So just geometry and material type. So in material section guess. So here you will see steel and apply. You can create your own material from this section. If you go, just click here and you can create material isotropic, orthotropic, anisotropic. Then if you see the show calculated inertia, it will show the what is the mass, what is the inertia. Okay, and continue. Okay, you can see here center of mass marker is created. This is the location of center of mass and you can see. So if I click center of mass, its orientation is 16.3.8340. So I will change orientation to 0, 0, 0. So it will be convenient for us to create the joints. So then similarly for pin, choose material type as a steel. You can choose different one. Okay, just I want, so center of orientation is 270, 90, 90. It's okay. That means it is along the proper axis, so that these coordinates are not inclined. Then connecting rod cover. So basically if you see, this is a connecting rod This is connecting rod cover, or you can say cap. So we can merge these two bodies. So first I will apply material to crank. Material type, yes, it is steel. Okay, now I will see what is the center of mass orientation. 270, count 90 here, 90, 90. Then we will merge these two parts. So I will hide it. I will make this part as a single one. So here in booleans tab, go to this merge two bodies. First body as cover, then choose second body. Now you can see there are two solids in this connecting rod section. Then apply material, then select, I will choose steel. It has created center of mass here. You can see its orientation is okay. You can observe. So center of mass is properly oriented for all the bodies. So for connecting rod center of mass, let's say it will be 360. Here it will be 90 and it again 360. So now we'll create the joints between two different parts. So we want to study the flexible body or connecting rod. You can choose other parts also, but I am choosing connecting rod. So for that, what will I do? I will create markers for connecting rod. So just I will hide these parts in. Okay, so what will I do? I will create markers at these two locations, at the center of small end and big end. So now if you see the location of center of mass in x direction, it is 2.6 10 raised to minus 7, almost equal to 0. But what will I do? I will make as a 0. Here also 4.9 e raised 10 raised to minus 6 means it almost 0. So keep at 0. Okay. So what we'll have to do? We have to create marker at the center and at the center also. So in bodies, go to this construction tab. Here we'll see the sign of marker. Choose marker, add to part. I will select this connecting rod and location. So it will prompt as a solid E71 center. I will right click. You can see at the center it will from this location, but it is not exactly middle, so it is at edge of the this hole. So I will modify this location. So in x it should be 0 and z it is already 0. So apply. Now it is at the center location and I will rename it. So marker 1 I will rename as a new name, small end marker. Okay, then similarly I will create one marker at center of big end also. Go to marker, add to part, select this connecting rod and it will prompt. So right click, choose the appropriate option, then modify it. So marker to rename, will give name as big end marker. Okay, now modify its location. So instead of 14 it should be 0, so that it will come at exactly center. Okay, now it is better. So now we'll create the joints between different parts. So first show all the parts of piston. So go to connection or connector tab. So first we have to create slider joint for piston. So choose translation joint. So I will choose piston head and second body as ground and choose a location at the center of mass. You can click right, choose piston head CM and orientation is along the piston vertical direction, so choose CM Y. So you can see symbol of translation joint. Then pin, so we will fix this pin to piston, so choose fix joint between pin first part, then right click second part as a piston head and location I will choose center of mass of the pin. Then then what we'll have to do, we have to create revolute joint between piston and this pin. So choose revolute joint. So you can see this orientation of the grid is in XY plane. Our revolute joint would be in YZ plane, so I will change the orientation of working grid orientation YZ plane so that joint will be created in this plane. So choose this one, revolute joint. First body is a connecting rod, right click and choose. Then second body pin location, we will choose that marker, small end marker that we have created. So here you will right click, you can see this first one, connecting rod small end marker. Then we have to create one revolute joint between piston and crank, so show the crank, then choose revolute joint. First body as a connecting rod, second body as a crank, location, so right click, you will see connecting rod big end marker. Now it is okay. Now we have to create revolute joint for this connecting rod. So choose one, first body as a crank, second body is a ground, then location will choose this at this center, right click, so crank solid B85 center. Okay, now we have created the joints. So now we'll give some motion to this crank. So go to in motion tab, choose rotational joint motion, select the joint, so I'm selecting this joint 5. Now go to the motion tab, I will modify, so instead of displacement I will choose velocity. So velocity, just I want 2 rotation in 1 second, so 2 rotation means 720 degree. So for just simplicity I will choose this 720 degree and click OK. Now just will try to run it for 1 second. End time choose 1 second. I will choose step size as 0.01 and run it. Okay, so mechanism is working now properly. Now we have to make flexible body. So what will I do? I will just first I will reduce the size of this icon. So you can go to in setting, here you can see the icons option. I will put new size as a 10, current size is 50. I will change new value on, then OK. So you can see the size of the various symbols and icons has been reduced. Then just go select all the bodies, right click, click on appearance, name visibility you can make off, so that all the text or name of the bodies will be invisible. So now we will convert this connecting rod from rigid body to flexible body. So just go to in connecting rod, you can see there are 2 solids in connecting rod. We have to make one solid. So for that, once unless and until there are one single body, it will not convert into flexible body. So for that you can have option as unite 2 solids. So just click on this option, here choose For that, right click, then connect first solid as a connecting rod, solid 3, and OK, and second solid as a this connecting rod, solid 2, and OK. Now you can see there is a single solid created inside this connecting rod. So now right click here, make flexible, choose create new option. So choose number of modes as let's say 10, and stress analysis. You have to choose number of modes more than 6 because first 6 modes are rigid modes. Then no stress analysis, then go to advanced settings. So here you can see element type as a solid, then element shape tetrahedral, it has only one option. Element order you can choose linear or quadratic, we'll choose linear for simplicity. Element specification you can choose size or, but for that right now we'll keep as a auto size. Element shape, instead of straight we'll choose mixed one, straight, curved and mixed one, because at the curvature it has to be curved and at a straight it should be straight, so it would be mixture of both types of solid. We will choose mixed one. Another type you can keep as it is, so here you can so choose, make these two options on. You can observe that there is a new body name is given to this connecting rod flex, it will be automatically generated. You can choose of the color of the body, I will keep as a green, then click OK. So it will take little bit time based on computer processing. So it will show the progress of the meshing. We can wait for some time. Now you can see there are 1488 number of nodes, elements, these many. So finally you can see replace process successfully completed, replacing rigid body with flexible body. So if you get this message, that means your model is okay, otherwise you will get some error, then close it. So you can see this rigid body is now deactivated and new body is created. So here you can go to modify section, you can observe the its mode, various modes. So if we see fifth mode, you can see frequency is almost 0. Sixth mode, again its frequency is almost equal to 0. So the first 6 modes are rigid modes. So beyond that, let's say 8th mode, you can see the frequency, you can animate this. This is a mode shape basically, so it's okay, cancel it. So we will observe this body, I will hide other bodies. So if you see here these locations, it has been properly created at the center. You can create a wireframe view. Now show all the bodies, we will run it. Simulation, go to 1 second, I will uncheck this update graphic display so that it will run in minimum time. Start the simulation. Now simulation is completed. Now we'll run it animation. So you can see the behavior change of this connecting rod. So what will I do? So just I will apply some force on this piston. If you see in engine there will be combustion force, so we will apply that and we can see the what are the stresses coming into connecting rod. Just go to force tab, choose this force, select the body piston head, location as a piston head, center of mass and orientation along the CMY. So you can observe this in the force tree, symbol is upward, so force should be in downward direction. Let's say modify this force. I will apply this force gradually, so I will create step function. When time is 0 it will be 0, when time goes to 0.5 second force will be, let's say, 1000 Newton. You can something step, so I will have to choose variable time, then okay. Now I will rerun simulation for 2 seconds. Now run completed. I will change the background to the white so that we can see the contour plots. Now see the animation. So this red arrow indicates the force on the piston. So to better visualization, I will change the transparency of this piston head appearance. Change the transparent, let's say 80%. And for crank also I will change transparency, let's say 80%. Then run this animation once more time, so we can observe these changes in the color pattern. So for pre-processing, so just in plugin go to the durability. So there will be option, first we'll create hotspot table. So in this we can see what are the top maximum values of stress or other parameters. So choose flexible body as a connecting rod. Analysis, I will choose analysis as the last one. I will choose the type, so you can choose different types. So I will choose one message. Radius, just type 5 and count is 10, that means it will show top 10 stress values. So you can see maximum stress value 7.7 Newton per mm square. So we have applied very less force, so that's why it will be very low value, but it is okay. And you can note down these node IDs 1.356, 1.428. Just choose 1356 and close. Go to the result, here post processor. So in post processor I will choose two windows. In one window I will load the animation. So here it has created plot of deformation. You can choose another one. So here go to counter plot option, choose one message stress, so it will show. Then graph, just go to connecting rod flex, or here in bottom you will find some result set. Choose here connecting rod flex, crank, joint pin. So we'll choose that node first. Go to durability, go to nodal plots. So last run analysis, flexible body as a connecting rod, select the node. So from hotspot table we see that node number 1356 was the node which is having highest stress value. So you can choose these options. Okay, then object, from here measures or result set, connecting rod flex stress. So node number 13561 MSC stress, add the curve, so it will show the stress value of that node. So it is fluctuating one because of this cycle. I will change counter plot from 1 MSC to, let's say, deformation. Then just run the animation. So like way you can create these flexible bodies and analyze its dynamics while it is in motion. So thanks for watching and subscribe to our channel, share as many as possible, and thanks for subscribing this channel and keep watching. Also you can put in comment section which mechanism or which type of machine you want to simulate in Adams. We will try to do that for you. And thank you. You can find the files for required for this tutorial in the comment description section. I have attached the link for these files. You can find the parasolid geometry at this location. You can download from this and try it on yourself, or just create your own assembly and try it. So thank you. We'll meet in next